Welcome back to Advanced Game Development Tutorials. I didn't publish any tutorial for 1.5 years now, but we're back now with Framebuffer Effects. You might know from old school RPGs like Legend of Dragoon or Final Fantasy. Yeah, I didn't have a lot of time in the past months and years, but now we're back. Let's go. So what is a frame buffer effect? And I figured the best way to explain this is to just show you how they look like in different games. This game is called Legend of Dragoon. It was a popular PlayStation 1 RPG, and it also employed frame buffer effects, and let me show you. Another game is Final Fantasy VIII, also Final Fantasy IX, also for the PlayStation 1. So I think you are able to see that it is an effect that is used as a transition between different stages of the game. In the games I showed you, it was the transition from the regular overworld to the battle, and it hides the loading process of the battle scene. And the only thing necessary to create this effect is to copy the texture when we want to load the different battle scene, and then to apply basic image operations on this texture. And we can do this, of course, in a shader. So how would we be able to achieve a frame buffer effect in Unity? The first thing we need is to render the contents of the camera into a texture, into a render texture, more specifically. And afterwards, we have kind of two options, maybe even more, but two ways you could do this that are kind of equal and similar is on the one hand to use a fragment shader, and on the other hand to use a compute shader. And the difference is very small, so you can do both things. It doesn't really matter. If you decide to use a fragment shader, you would set up a post-processing effect, and then you would use the texture you copied in the fragment stage of your shader, and you do some operations, and you will get a result. And after you get the result, you copy the result into a texture again, and you give the texture again into the shader, and you do that repeatedly, and you will get this frame buffer effect. And on the other hand, we can use a compute shader, and the way we will do it is also very similar. It's basically post-processing without using Unity's pipeline. Essentially, we are creating a quad, a mesh that is a rectangle right in front of the camera, really close, and we assign it a material that is not affected by light, and give it a texture. And then all we do is to do operations on the texture using a compute shader. And we also do that repeatedly, again and again. And in the same way, we also create this frame buffer effect. Don't worry if it doesn't make too much sense right now. We will create this effect, one that is similar to the Legend of Dragoon one, and it will make a lot more sense then afterwards. I have already set up a scene in Unity that contains a player and a camera, and the idea is now to transition to a new battle scene. And in order to do this, we need to set up the quad as described before, and we're going to do that in code, and for that we need a script. And I also already have created a battle transition script, and I'm going to show it to you in Visual Studio. As you can see in the script, we don't have a lot of code yet. What we now will have to write is a method that copies and renders the scene into a render texture. And on the other hand, we want to create a quad that has an unlit material, and we assign the copied render texture, the screen render texture, to that quad and scale the quad accordingly so it fills the whole screen. But first of all, we need a camera component. That is why I have added a getCamera method. And in this case, we put the quad below the camera. So we are searching for a camera component in the parent. But in case you put it anywhere else, you just search for the main camera in the scene. And then we return the camera. We need the camera for two purposes. For one, to know from which camera we have to copy the contents. And on the other hand, we need to know what is the field of view of the camera to be able to scale the screen quad appropriately. Now we will write a method to copy the screen into a render texture. The first thing is, of course, to get the camera. And the next step will be to create and scale the render texture to be the same resolution as the camera. Here we get the resolution of the camera texture. It is scaled based on the dynamic resolution. And if we already have a render texture, because maybe we already started a transition, then we will release the render texture again and destroy the object as well. And otherwise, or afterwards, we will create a new render texture, a temporary render texture, with the resolution of the camera. So it will have the same amount of pixels as the camera resolution. And we just want to have our color texture. And also very important, we don't want to use gamma as our texture color mode, but we want to use linear colors. And we need to make sure that random write is enabled. Otherwise, we cannot really work with the texture in a compute shader setting. And the last step is then to simply create that render texture. We set the target texture of the camera to the screen render texture. Then we render the camera, and then we release the target again, so the camera renders as usual. And afterwards, we are basically done. The screen render texture will now contain the same image as if we would have rendered the scene regularly on the camera. The question is, why do I want to return another render texture if the screen render texture is already a private field? And the reason is that that actually we need two render textures, one for displaying and one for working with, and so we need to deploy a buffer texture, and we are going to create one now. So one nice thing about render textures is that they have descriptors, and we can just access this descriptor and create a new render texture using the descriptor, which means we basically are copying all the attributes of the render texture. In this case, what is the width of the texture, the height of the texture, and just for safety reasons, we also make sure that the random write is enabled, because we also want to use it in a compute shader. Then we create that new texture we made from the descriptor, and the last step is to copy the screen render texture we rendered into before to that copy texture, so now both contain the same contents, and we return the copied render texture. And with those two textures, now we can actually start to use compute shaders. But first we have to create that quad. I have added two new public fields. One is for the ScreenFX quad game object, which is the game object that contains the quad. And the other one is an offset, which is the offset we are going to put the quad in front of the camera. So there's a near clip plane and a far clip plane for the camera, and we are going to put the quad to the near clip plane plus a little bit of an offset, so that we don't run into trouble with C-fighting. I have added a new method, setup screen quad, and again we are fetching the camera of the scene. And also important, we need to know the near clip plane of the camera, and now we will position the quad accordingly. We need to set translation, rotation, and scale. Translation or position we can do in the following way. We calculate the distance the plane should have from the camera, how far should it be in front of the camera, and we do that by taking the camera position and then adding the plane distance times the forward vector to it, and this gives us our final position of the quad. The rotation is handled automatically. Why? Because it is it is a child object of the camera, so whenever the camera rotates, the quad will also rotate, so this is already correct. The only thing that we now have to do is to calculate the scale, and this is maybe not as easy to understand, but it is also not very complicated. Remember, view space, bottom left is 0, 0, and top right is 1, 1. And so what we can do is to use this method of the camera, which is called viewport to world point, and we just give it these coordinates 1, 1, 0, 0 with the plane distance. And what that will return is the projected point on the near clip plane. So what would be the top left corner of the camera in world space at the near clip plane position? And what that allows us to do is to calculate the width and the height of the near clip plane in world coordinates. And we can do that by projecting them onto the right vector of the camera and the up vector of the camera. So we are projecting this vector onto the sides of the camera, and then we know the width and the height of the near clip plane in world coordinates, and this is equal to our scale of the quad. If that doesn't make too much sense, don't worry. The important thing is that this will always scale this rectangle so that it fits exactly to the camera with just a little bit of an offset, so that it is not exactly at the near clip plane. As the last step to set up the screen quad is to get the mesh renderer, then get the material of the mesh renderer, and then to set the texture to our screen render texture. And in this way we have assigned the copied texture we are working with in the compute shader to the screen. And you can see in Unity here underneath the camera is the quad, and it has assigned a special transition material with a special screen shader. But this is a very simple one. I made it in shader graph, and the only thing it does is to sample a texture. In our case, this will be the screen render texture, and then that is the only thing it does. So there is no light effects, nothing at all will ever affect this shader, and now we can start to program our compute shaders, and we will start with the horizontal effect that is similar to Legend of Dragoon. Coffee break. Let's start by creating a new compute shader. For that, right-click any folder, create shader and compute shader, and open up the script. I have already added some fields and functions to my shader. The important thing is to have a texture, a copied texture. This is the texture of the last frame, and a result which is going to be the texture of the new frame. And I also added a random function. This is a very famous one, just so that we can make it a little bit more noisy when we do our Framebuffer effect. So this is our effect. It is actually very simple. We have a scanline that goes from the bottom of the screen to the top of the screen, and we will increase the scanline in the code within an update method or a coroutine. And all pixels that are below the scanline in UV space will be faded out, while all the other pixels that are above the scanline will remain have the same content as before. And so over time, this means as long as the scanline is going to the top of the screen, all the pixels will eventually fade out. And we do something that is a little bit more than just fading out. We take the color of the pixel above, and we fade it out with a random factor that is dependent on the x coordinate on the screen. And then we also add a little bit of a burning effect by making brighter colors fade out less over time than darker colors. But essentially, this is the whole shader. Nothing too much to it. Calculate the UV coordinates and check what is the scanline right now. We still need to be able to dispatch the compute shader in our battle transitions script. For that reason, I've created a coroutine, horizontal transition. And we will also need some parameters for the execution of our Framebuffer effect. 3 parameters in total. First of all, we want to be able to adjust the rate of the fading out of all the pixels. We want to have an offset. This is the horizontal offset we are sampling the pixels from. So we are not necessarily taking the pixel right above to push it down, like in the effect you saw in Legend of Dragoon, but it could be a few more pixels up. And another parameter we want is the scan duration. How long does it take for the scan line to go from 0, the bottom, to 1, the top? So let's start. The first thing we do is to copy the screen. That is the method we have written before to get the content of the camera into the render texture. Then we set up the screen quad, and then we set the screen quad to be active. We retrieve the parameters, which is a public field. Then we get a shader instance. We want to have a new instance because we are changing the parameters all the time. So if we call this transition effect multiple times, we would have to reset the parameters probably. So since we don't want to do that, we just create a new instance and destroy it after the coroutine is done. We retrieve the kernel. There's only one kernel, so that is easy enough. And then we calculate the amount of groups we need in order for the compute shader to apply to the whole image. And this is done in a helper method that is pretty simple. It gets the thread group sizes, it gets the problem size. In this case, this is the resolution of our texture, and returns how many groups you need. After the whole effect is done, what we should do is to clean up. And in our case, we have created 2 render textures. One of them we can reuse, the other one we should destroy, that is the copy. And so here we release our temporary render texture again, and we also destroy the shader instance we have created for this effect. And then we set the quad to inactive again, so it is not visible, and we can render normally again with the camera. And in addition to that, so we have a setup phase and we have a release phase, and in between we have the actual effect running. And before we do that, we set the parameter, the offset, and then we are starting the main loop. So this timer will increase each frame with the unscaled delta time until the duration is reached. And the reason I have chosen unscaled delta time is that we don't want to affect any pauses or slow motion to change the screen effect. And why is that important? Because what is most likely going to happen is that you start the screen effect and then you want to pause the game so that the game is not continuously running and the player cannot trigger any more interactions. And so it is important to set it to unscaled delta time here. Lastly, we calculate a few more floating point values and assign them to the shader. In particular, how much we will fade out the pixels, and here we move up the scanline value. We assign the render textures to the shader, and then we dispatch it. And after we have dispatched it, we will split the screen render texture back to the copy. So basically we are copying the result into our temporary buffer again, so we can use it again in the next iteration. After we have assigned the compute shader and played around with the values a little bit, we can get an effect like this, which is already then relatively close to where we want to be. I have added 2 more parameters for sampling the texture not only from above but also a little bit to the left and to the right. So we get a little bit of a smoothing effect as well, so that it's not as noisy as before. And this is how it looks now. And here is the final code of the shader, and yeah, it is almost the same as before. So now we've created a horizontal effect, then the next thing we can do is to create a vertical Framebuffer effect. Since this would be a little bit boring, we add a few things. Namely, once we add a little bit of noise to make it more interesting, and the second thing we add to make it more interesting is a little bit of a saturation effect. So again, we create a new compute shader. This time we will call it vertical. So I will simply show you the final vertical Framebuffer effect code. Most of the things you have already seen. We have a scanline, we have a fade. New addition is that we also have a kind of saturation. And we have a noise buffer that we filled with some Perlin noise that we sample from to create more variation. You will see it soon afterwards. And we have our 2 render textures as before. And like before, we are calculating the UV coordinates, and in addition to that, we are actually also doing a bit of noise here to create a different UVX coordinates depending on the horizontal on the vertical position of the pixel. And what that does is to create a kind of a curve you will see later. So the effect starts differently for different pixels depending on our noise buffer. And we will increase the scanline again from 0 to 1. In this case, actually from negative values to even more than 1 value, so the effect has a little bit of a delay. And all we do is to copy and do the fade like before. And otherwise, if the pixel is not below the scan line like before, then instead of just copying the same color over and over again, we will saturate it to kind of brighten up the color. And what we do is to calculate the hue, saturation, and value of the color. And we only are interested in the luminosity of it, and then we adjust the color so that it brightens up over time. And this will give us a very interesting effect. You already saw it in the video, and we just need to fill up this buffer in the code, and I will going to show you now. The coroutine looks very similar. We copy the screen, we set up the quad, we activate the quad, we get the parameters, we create an instance, we get the kernel. That is all the same. The only difference is now that we create a noise buffer, which is a graphics buffer, so it is just an array filled with floating point values. And what we're actually going to do is we create a floating point value for each pixel in the y-axis, so for each pixel in the height, we create one noise value, and we just assign a Perlin noise with some parameters and a little bit of a scale to create kind of like a curving effect. And you can see that later on in the video. And then we set the data for this buffer, and we set the buffer to the shader. And otherwise, the loop itself is very similar. The only difference is that we have now a few more parameters, but otherwise it is almost the same. And also the destroying, yes, parenthesis is missing. Otherwise, destroying the render texture, destroying the shader instance, and deactivating the quad again, it's all the same. And now I'm going to show you how it looks like. So I've played around with the values again, and I've added the vertical compute shader here, and this is what we get. By the way, if you want to have a look at the complete code, you can just go to the GitHub repository and you can find the whole source code of today's tutorial, but from all tutorials from the past as well. You have to notice that, so since this is now a little bit of a longer project, the whole tutorial series, some of them are with Unity 2022.3, and the newer tutorials are with Unity 6, just to let you know. Alternatively, I've published a collection of effects into an asset on the Unity asset store, and you can just download them, import them to your project, and use them directly. That concludes the tutorial. I hope you were able to learn how to make Framebuffer effects, and maybe you will make a few of them on your own in the future. And yeah, hopefully the next tutorial will not take 1.5 years to make. And on that note, we see each other soon, and goodbye.